The Saturnian system is an absolute wonderland.
Saturn just makes us gasp at its beauty.
Saturn, as the second largest of the planets, it's nearly 800 times the volume of Earth. A true gas giant, known for its mysterious, captivating rings. Almost 72,000 miles in diameter, the ring system is barely as thick as a football field is long.
The rings capture the imagination to the point you have to understand where they came from and what do they mean.
To try and answer these questions, humans designed, built, and launched some of the most advanced spacecraft ever conceived.
It was and is the largest outerplanetary spacecraft that's ever been built.
This is a massive piece of machinery.
This is the story of the exploration of Saturn, its rings and moons.
To see something like that on a moon in the outer solar system, it was just spectacular. It still gives me goosebumps to think about all of that working so well.
The building blocks of life could form in the interiors of these icy bodies.
Titan is the most interesting moon in the solar system, hands down.
To the naked eye, the night sky is filled with points of light. Zoom in on almost any of them, and they remain just that, shining points in a dark universe. But one celestial object revealed itself to an Italian polymath that it was special.
Galileo wasn't the inventor of the telescope, but he was one of the first people to use it for astronomical observations.
It was 1610 when Galileo first observed the Saturn system.
His drawings showed what were described as ears or jug handles either side of the planet.
And so he thought, well, these might be moons, but stuck one on each side of the planet Saturn. He didn't know Newtonian mechanics hadn't been invented. He didn't know that moons have to go all the way around a planet.
When he went back to look at Saturn a couple of years later, he noticed that those features had gone.
Galileo even suggested that Saturn had eaten his own children, as in the ancient Greek myth, and that's why the moons had disappeared. Galileo lived in Italy, but he was aware of other major figures in his time, including Constantine Huygens from the Netherlands. And in fact, it was Huygens' son, Christian Huygens, who eventually solved the puzzle that was posed by the disappearing handles of Saturn.
Christian Huygens turned his telescope towards Saturn. As technology had developed, optics had developed, and he was able to see more.
And what he saw meant that he was able to come up with this radical idea that Saturn was surrounded by a ring system. And he was able to link back to what Galileo saw, because if the ring system was tilted at an angle to our view from Earth, it means that sometimes you'll see the rings tilted and you'll see them sort of almost face on. And other times when the planet has moved, they'll be edge on.
In fact, even today, when Hubble, the best optical telescope we have, looked at Saturn cross through the ring plane, the rings disappeared.
But not only that, Christian Huygens made another amazing discovery, that Saturn has a moon. And it turns out that this moon is a really curious place and is perhaps even more curious than the rings of Saturn itself.
After the discovery by Huygens of Saturn's first moon, Giovanni Domenico Cassini discovered 4 more in the next decades, and moons continued to be discovered over the next few hundred years. However, from the first, there were big questions posed by Saturn's rings. What were the rings made of? How did they arise? What's the origin of the rings of Saturn? And why does Saturn have rings and not the other planets?
The only way to answer that question is to actually get up close. We need to go to Saturn. But getting to planets in the outer solar system obviously requires a huge amount of fuel. So you start to think about, well, what are other ways that you can accelerate your spacecraft without requiring lots of fuel? And one technique that's used is what's called a gravitational assist.
It was discovered that the outer planets would actually align in a way that they hadn't since Thomas Jefferson had been president.
So we realized that you could fly past Jupiter, get a kick, go to Saturn, get a kick, go to Uranus, get a kick, go on to Neptune.
This gravity assist trajectory was called the Grand Tour.
And if we were going to go and do this, take advantage of this alignment, we better get going and launch that spacecraft soon.
NASA quickly responded to the opportunity by preparing some pathfinding spacecraft, one that would go to Jupiter and one that could use a gravity assist from Jupiter to go on to Saturn. And that was called Pioneer 11. When Pioneer 11 eventually arrived at Saturn, 6 years after flying by Jupiter, it was an immense, exciting moment. The rings of Saturn were big and beautiful in our pictures, and we stood in awe at the close-up views. My task was to see if we might discover any new rings. And amazingly, I watched the first images appear on the television screen, and there was clearly a new ring of Saturn. The rings of Saturn had originally been named A, B, and C in order from the outermost known ring to the innermost. But in the 20th century, we began to discover new rings, which were then assigned alphabetically in the order of discovery. First the D ring, then the E ring. So the next available letter was F, and so I named that ring Ring F of Saturn.
Pioneer 11 passed Titan by quite a large distance, a couple 100,000 miles away. And really, all it told us about Titan was that it was very, very cold, too cold for life as we know it to exist. But actually, we needed to go back and look at this thing in much more detail.
Fortunately, the next generation of spacecraft, the Voyager 1 and 2, were on their way.
The pioneers had told us it was safe. It's okay. We can go there. The primary purpose of those pioneers was really to pave the way for later spacecraft.
And that mission was called Voyager. And the Voyager mission had two components, Voyager 1 and Voyager 2. Each of them would get a gravity assist from Jupiter to go on to Saturn.
But that's then where the missions deviated, because Voyager 1 was given an extra special task. It was to go and visit the moon that Christian Huygens had discovered in 1655, Titan.
Titan would become almost as important a destination as Saturn itself.
This is a massive moon, probably not worthy of the word moon. This is a body which is bigger than Mercury, so it's a big moon.
The atmosphere of Titan was hinted at a century ago and confirmed in the 1940s. It's the only satellite in the solar system with a dense atmosphere. In fact, its atmosphere is actually denser than our atmosphere here on Earth.
Titan is the most interesting moon in the solar system, hands down.
But getting to Titan meant a change of direction, shortening the exploration of the outer planets.
So Voyager 1, going off to visit Titan, meant that it was no longer able to slingshot on to visit Uranus and Neptune.
If Voyager 1 had not been able to achieve that objective for whatever reason, Voyager 2 was going to be diverted to do that job at the expense of going on to Uranus and Neptune. But that's how they felt about Titan, the importance.
So just a year later, Voyager 1, equipped with better instruments and better cameras, was preparing to take a look at Saturn and its rings. The encounter was an amazingly thrilling and rapid experience. all happened within a matter of a few days. And even before you could explain some of the new phenomena we saw, Voyager was off on its way out of the solar system. Many people referred to that flood of data, the camera pictures and other observations, as like drinking from a fire hose.
The learnings from the Voyager spacecraft fundamentally changed our understanding of the Saturnian system.
After the Voyager flybys, we knew there were thousands of rings, and it's that moment that we stopped naming them with letters. It was just impossible. It exceeded the alphabet. A ring could be maintained between two moons, one outside the ring and one inside the ring.
And that's the beauty of this idea of moonlets that are sitting within the rings, shepherding the gravitational motion of the particles within it.
Maybe it's a scientific prerequisite to start with a simple idea, but we had imagined the rings were ancient, unchanging, and completely uniform. All were immediately questioned.
But what was the origin of the rings? Where did they come from?
When an object gets closer to the planet, it gets stretched out, and so a basketball might look more like a football under this stress. The question is, can that stress be withstood by the object? For most competent objects, including humans, we can withstand that stress. For objects that are piles of rubble or dust, or are big, say larger than 50 or 100 kilometers, they cannot withstand that force.
If a large moon had once strayed too close to Saturn, this destructive force would have been enough to tear it into tiny pieces.
So if Saturn once had a moon, say an object about the size of Titan, if it were dragged in toward the planet by friction, first the ice would shatter, and then later the core, which is made of metal, would shatter or might even end up inside the planet, and the pieces of ice formed a ring around Saturn.
And now the mission turned to what scientists deemed worthy of missing out on Neptune and Uranus for: Titan.
The scientific community and the public watched with great interest as Voyager 1 made the first flyby of Titan.
There was an organic haze that encircled the surface, and you couldn't see the surface as a result.
That atmosphere is simultaneously the bane of my research because it blocks the surface, but it's also the reason why Titan is so interesting.
One of the other things we figured out was that there was methane present in the atmosphere of Titan. This opened the really, really tantalizing possibility for lakes and oceans on the surface.
Some people think that if we look in these methane lakes, perhaps we'll find a different way of organizing matter, a different way of organizing life.
Titan was still hiding all its mysteries from us. So that laid down the gauntlet of the challenge. We must now go to the surface of Titan.
Fortunately, Voyager 1 made excellent observations of Titan. So thankfully, Voyager 2 was allowed to go on to the next planet, Uranus, and then to Neptune. The Uranian rings had been discovered from the ground in 1977. Voyager itself discovered the ring of Jupiter in 1979, and while we were on our way to the planet Uranus, the rings of Neptune were also discovered. So by the time the Voyager mission had completed, we knew that all of the giant planets had rings, just the opposite of what the question had been before those missions of why only Saturn has rings, but leaving us with deeper questions about Saturn's rings. What were they made of? How old were they? And why are Saturn's rings so particularly different, so big and so bright compared to the narrower, less massive, darker rings of Jupiter, Uranus, and Neptune? Those could be addressed by a mission that went into orbit around Saturn and stayed for many years.
We already knew that the value of orbiting a system And the amount of understanding you can gain by being there for a long period of time is so amazing that the next step was clearly going to be an orbital mission.
And if we're going to send another mission to Saturn that stays there, it should have a part of it that lands on the surface of Titan.
Planning began in 1982 for an exploration that would be more ambitious and advanced than anything that had gone before. A mission called Cassini-Huygens.
The spacecraft was about the size of a school bus. If you just looked up, it was a monster.
It was and is the largest outerplanetary spacecraft that's ever been built, and may, in my lifetime, ever be built.
T plus 20 seconds.
The mission was a collaboration with the European Space Agency, who designed and built a lander called Huygens.
The Huygens probe was actually designed to be able to float in liquid as well as land on a solid surface, because we didn't know at the time whether it was going to land in a liquid or on a solid surface.
So we designed a mission to cope with as many characteristics as possible.
No one's ever tried to measure the depth of an ocean and how hard a rock is, depending on which one you're going to land on.
We knew from Hubble images that there probably wasn't a global ocean, but whether there were other liquids was still not known. Huygens' team had to prepare for that, but also a very hard landing, or maybe you can imagine a very squishy surface full of organic goop.
20 seconds and counting. This is Titan Launch Control.
Without any doubt, the most risky element of any space mission is the launch.
T-minus 15 seconds.
It was a nighttime launch, so you had to get on the bus something like 2 in the morning or something to go out. And we did that, and we went out to the launch site, and the first opportunity to launch was scrubbed.
Seconds and counting. This is Titan Launch Control.
Without any doubt, the most risky element of any space mission is the launch.
T-minus 15 seconds.
It was a nighttime launch, so you had to get on the bus something like 2 in the morning or something to go out, and the first opportunity to launch was scrubbed. And so we did the same thing again 2 days later.
T-minus 10.
When you put 8 years of your life into designing and building and testing something which is going to go into space,
9, 8,
and then seeing it on the top of a rocket as being vibrated and accelerated on its way to Saturn, it is quite a feeling.
1.
When it did go off, it created a huge amount of light, and then the rocket went behind a cloud.
When it went behind that cloud, it was very impressive. The whole cloud lit up.
We all thought, oh goodness, has something gone wrong?
And then the nose cone came out, and you went, whew.
Go ahead, S02E01.
One of the things you have to do when you arrive at a big planetary body is slam the brakes on pretty quick. You typically do this by going very close to the planet to slow you down, so you get captured by the gravitational pull of Saturn.
It was an incredibly complex sequence that we had basically worked on for 2 years.
Even after Pioneer and Voyager, we didn't know enough about the possible dangers of the Saturn system. And because the Cassini spacecraft was moving at about 10 miles per second, even hitting a grain of sand or a chunk of ice could be deadly to the spacecraft. And the best was to turn so that the spacecraft antenna was facing forward.
The high-gain antenna, which is the thing which communicates back to Earth, was actually protecting it from potentially being hit by dust particles. So it couldn't be in communication with Earth at that time.
Once Cassini had crossed the plane of Saturn's rings, the spacecraft had to reorient itself again.
The thrusters had to be turned so that they would point in the direction of motion to be able to capture it into orbit.
During the 90 minutes that Cassini's engines were firing, the spacecraft was completely shielded from Earth. At its closest approach, the spacecraft was just 12,427 miles from the cloud tops of Saturn. All the mission controllers on Earth could do was wait.
We all held our breath, waiting for the signal to return. But then we got a signal which was dead on. And we knew at that moment we had successfully gone into orbit.
It was really a fist pump moment.
When the burn was completed, we knew we were in orbit. So we turned away from the Earth and photographed the dark side of the rings. And then after we come back through the ring plane crossing again, we turned back to the Earth to start to play back that data. And those images, I'll never forget them.
Cassini-Huygens had arrived at the Saturnian system, an enormous gas giant with 82 moons that we currently know of, orbiting on the outside and within the hundreds of rings.
From a mission engineer's point of view, the rings are a hazard. But once we've discovered that the environment's safe, then we can start to open up the stops a little bit to allow more activity.
We knew that we'd have long consecutive pieces of data to test our theories, but we didn't realize that because we could orbit Saturn hundreds of times, the same aspect could be seen over multiple times by all the 12 instruments.
It's very easy to think of the system as isolated parts, especially when you're working with a spacecraft mission and you target this feature and then you target this satellite.
Any speculation, any idea we had had from the years between Voyager and Cassini could now be tested.
And as for the origins of the rings and the moons, the Cassini team made a further discovery.
As we have seen quite clearly, Saturn's rings are made out of ice, which is the fragments of shattered icy moons. But the alternate is also true. Cassini showed us that the pieces of the ring are sticking together to make new moons. So the rings are collecting in places to make moons, and the moons are being shattered to make new rings. So this is a sort of a cosmic recycling of material.
So not only are the rings of Saturn most likely made of moons, but they also make new moons.
One of the best measurements that Cassini made was to measure the total mass of the rings. This determines how long this recycling process can go on. The combination of those two facts say that the rings are about 100 million years old. This can be extended perhaps to 1 billion years or two, but the current one is the rings that the dinosaurs would have seen. If we were to look closely, many of the ring particles would appear fluffy to your hand. But occasionally, particles will hit each other at a much higher velocity, which will knock off a spray of small particles of snow and ice, which eventually are recaptured by other clumps. So the equilibrium, the balance between these two processes, leads to a distribution of sizes from dust to mountains, and each of the objects being like a pile of rubble with a coating of snow on the top.
After 6 months in orbit, Cassini was scheduled to deploy the Huygens lander on December the 25th, 2004.
We had Christmas dinner at my home and we had a lot of the European and American contingent because we were all spending Christmas at JPL. A few days later, we turned around to take a picture of where the probe was supposed to be. It's a little speck. It's not very exciting, but it was a genuine confirmation it was exactly where we thought it was going to be. Because what happens with the probe is essentially when you release it, you've turned on a little 3-week egg timer. Your worst nightmare is silence. That's happened too many times to people in space missions, and it's just a punch in the gut.
After 6 months in orbit, Cassini was scheduled to deploy the Huygens lander to Titan on December the 25th, 2004.
Your worst nightmare is silence. That's happened too many times to people in space missions, and it's just a punch in the gut. But 3 weeks later, right on schedule, we get the signal back.
When we arrive at Titan, we're traveling at incredible speeds. And what you got to do is go from ballistic, incredibly fast speeds at the top of the atmosphere to 0 speed at the bottom of the atmosphere on the surface. And this is pretty hard to do. There are several elements in order to get yourself down to the surface. The first is a heat shield.
Titan has a huge atmosphere, and Huygens was just screaming in.
And if we will send the probe without protection, it will burn immediately.
So you have the sacrificial heat shield in front of the probe. So the fireball that's created as the probe slows down doesn't destroy the lander itself.
And in the case of Huygens, the heat shield was made of many of those tiles.
While the heat shield was slowing the probe down, Huygens experienced a deceleration of 15 Gs. Once it had gotten to an altitude of about 110 miles and had slowed to nearly 1,300 feet per second, Huygens deployed the first of its 3 parachutes. The pilot parachute stabilized the probe and pulled off the back cover, which deployed the main parachute. At this point, the used-up heat shield was discarded.
But Titan's atmosphere is so thick that if we kept that parachute on, the batteries would have run out before it got to the surface. It was going to go so slowly. So it actually deployed that parachute and then dropped the last chute, which allowed it to descend at a more reasonable pace.
You get horizontal winds coming across and swinging the probe about.
The images from descent show channels on the surface. And it was just so spectacular to see something and know what it was on the surface of Titan, and for it to be river channels.
It then landed on the surface and it started transmitting back to Cassini, which was way up overhead.
The spacecraft, meanwhile, is flying over the top and pointing at the point on the surface of Titan where the probe is. And eventually the spacecraft goes over the horizon. The batteries were still going, even after we lost sight of it. The spacecraft turned back and started to play the data back. The imaging guys turned around an image of the surface very, very quickly.
And it flickered up on the screen.
And everybody looks up and goes, what's going on here? You know, it was almost like it was fake.
To see something like that on a moon in the outer solar system, it was just spectacular. It still gives me goosebumps to think about all of that working so well.
It was sitting on this flat lake bed, and the things that appeared as rocks in the background were actually pebbles of ice that had been frozen.
Titan is an icy satellite. Its bedrock is made of water ice.
But when we look at the surface of Titan with the spectrometer, it's actually really hard to find any pure water ice spectral signatures. And I think that the key there is all these atmospheric products that are continually falling out across the surface.
Titan's atmosphere is actually mostly nitrogen, like Earth's atmosphere, but it's cold in the outer solar system. And the next most common constituent in the atmosphere is methane. And methane in Titan's atmosphere plays a role very much like water on Earth. So the methane in the atmosphere can condense to form clouds. It can actually rain out onto the surface. It can run across the surface in rivers, form lakes and seas. So it really does have a complete hydrological cycle where methane plays the role that water does on Earth.
Carl Sagan and his research partners, Carre and Thompson, gave us a really interesting insight by doing experiments where they mixed nitrogen with methane and then provided some free energy source, some light or some particles, to break them apart or to ionize them. And it led to this incredible organic chemistry that was beyond the wildest dreams, created this stuff in the laboratory they call tholins.
The methane dissociates at the top of the atmosphere, recombines to form very complex molecules, and all of that material falls out onto the surface.
How long that process has been going on is still not well understood, but if Titan has had an atmosphere like it has today for the entirety of the solar system, That's going to produce a volume of sediments that means that Titan's crust is not just water ice, but also has a bunch of organic sediments that have been built up over time.
All of these organic materials have been sitting around, littering the surface of this moon, where there's the opportunity, potentially, for them to have mixed with liquid water.
If you react water with these precursor molecules, what's been demonstrated is these tholins that have been studied in the lab can form amino acids.
And the universe provides us that mechanism when impacts hit the surface of Titan. Because every impact has enough kinetic energy to melt some of the crust. The bigger your impactor, the more kinetic energy you impart, and so the more melt you can generate. And then based on how much melt you generate, you have this pool of liquid in the near subsurface that's going to cool slowly over time. And based on the sizes of impact craters that we've seen on Titan, this can be anywhere from hundreds to tens of thousands of years.
And it's been doing these chemistry experiments for hundreds of millions of years. So we know that Titan has all the ingredients necessary for life as we know it. So we know that Titan has all the ingredients necessary for life as we know it. And it's been doing these chemistry experiments for hundreds of millions of years. You also have the opportunity for organic material to mix with a different solvent in the form of liquid methane. And so perhaps there are other prebiotic systems on Titan that have progressed that are completely alien to the water-based biology we have on Earth.
It's hard to conceive how a methane-based form of life would work, but nature has repeatedly surprised us, as demonstrated by all the findings of the Cassini mission. Certainly it would be very exotic. And at present, we have no indications in any of the current measurements from the Cassini or Huygens part of the mission that there was anything bizarre that we might need to attribute to the activity of life.
But the only way to find out is to go and look. So you have with Titan this wonderful possibility that we might find life as we know it, or we might find life as we don't know it.
But as exciting as Titan was, there were even more intriguing discoveries to be made.
When Cassini was approaching Saturn for the first time at the end of 2003, our experiment, the ultraviolet imaging spectrograph, was systematically scanning back and forth the planet Saturn. And we were amazed to discover that the system was filled with molecules of oxygen. And the oxygen was completely unexpected. And we noticed that the peak in the distribution was just a distance 4 times Saturn's radius from the center of the system. We knew that the moon Enceladus was orbiting just at that distance.
Enceladus is a tiny moon, just 313 miles in diameter, with a surface area slightly larger than Texas. It coexists with one of Saturn's fainter rings, the E-ring.
The E-ring is just a ring of icy grains in the micron range. It was tenuous enough ring that we could fly through it and examine it. We had these tentative ideas that maybe there was a connection between the E-ring and Enceladus because they were pretty co-located. But we didn't really have any understanding of how they were playing together.
Enceladus originally was on the itinerary, but only marginally so. It was another very interesting Saturn moon. Small, very shiny, very white, very bright. But other than that, pretty much too small to be interesting.
And it was in the first close flyby that the magnetometer team detected something interesting that they didn't expect.
The magnetic field instrument observed that the magnetic field lines didn't quite come down to the moon the way they should. The magnetometer team said, it looks like it has an atmosphere. Well, anybody that knows anything about moons says that's too tiny. It can't have an atmosphere. It's way too small to hold onto anything.
A moon as small as Enceladus has a tiny gravitational field, far too weak to hold on to an atmosphere. And bizarrely, the atmosphere that was there did not seem to be evenly spread out.
If you flew by the South Pole, it looked like there was an atmosphere, but if you flew by at the equator, you didn't see anything at all.
But then we went back again and again, explored with more instruments, and then took some images. And all of a sudden realized that not only it had an atmosphere, it was an icy atmosphere, but it had these plumes coming out of the southern pole.
And here's water geysers, on a tiny moon.
And that water that was coming out of what we later found out to be an interior ocean was what was forming the E-ring.
We were able to measure the amount of water in those plumes, exactly enough to explain the ring of oxygen around Saturn that we had seen before that approach.
And as we flew through these plumes coming out of the South Pole, some of that plume material was captured by the instrument.
And we used that to learn more about the interior ocean chemistry. Not only did it contain water vapor, but it had traces of ammonia, methane, H2, CO2, and then there was a whole host of organic compounds that we could also see.
The experiment that we did here at Colorado, we watched a star set through the plume. And now we can put all that information together to get a picture of the shape of the eruption and also the material that's being erupted from inside of Enceladus. And amazingly enough, that material has the basic building blocks of life.
We've been dominated as biologists with a fixation on the idea that all life on Earth is powered ultimately by the sun. Any formation of life going on Enceladus is going to be happening beneath the icy crust in the oceans underneath, where we see the same kind of hydrothermal vent systems releasing hydrogen gas into the oceans there, which we know for a fact would have been present on the early Earth, and they don't strictly require the sun.
We think, based on the types of molecules and other chemicals we're finding in the plume, that this process called serpentinization is happening. It's a fancy way of saying how liquid water can react with rocks. And serpentinization is thought to be really important for supporting microorganisms and the base of an ecosystem outside of these hydrothermal vents, because it makes abundant hydrogen. And hydrogen is sort of like rocket fuel for a microorganism.
This says to me that would be a good place to go. Measure those plumes, maybe drill down and see if there's any form of life there.
So Enceladus may have just the right conditions for life to get started, far away from the sun. And the evidence for its mysterious inner workings can be seen in the enormous, diffuse E-ring. Cassini would spend more than 13 years at the Saturnian system and complete 294 orbits of the planet. But eventually, its fuel would run out.
Everything has to end, including Cassini.
Cassini would spend more than 13 years at the Saturnian system, but eventually its fuel would run out.
Everything has to end, including Cassini.
We went through this amazing time at the end of the mission, ending up with orbits which went inside Saturn's rings. But we knew at the end, of course, that the idea was to actually burn the spacecraft up in the atmosphere of Saturn. And that's to avoid it hitting these astrobiologically feasible places like Enceladus and Titan. The last thing we would want to do would be contaminate those with something sent from Earth.
The spacecraft was oriented so it could communicate with the Deep Space Network here on Earth, but then the other axis was set so that the spacecraft could get the best measurements of Saturn's atmosphere as we plunged into it.
We have lots of signal at X-ray band and Sierra band.
Call loss of signal at 115546 for the S band, so that would be the end of the spacecraft.
I don't think any of us were ready. Have you ever had pets? And I've gone through 8 cats and 2 dogs during the 23 years I worked on Cassini. And when you know it's time, it's time. And it was timed in the spacecraft.
Signal from the spacecraft is gone, and within the next 45 seconds, so will be the spacecraft. I hope you're all as deeply proud of this amazing accomplishment. Congratulations to you all. This has been an incredible mission, an incredible spacecraft, and you're all an incredible team. I'm going to call this the end of mission. Project manager, off the net.
I've always loved the rings of Saturn. The Cassini exploration has allowed us to see them really close up, changing before our eyes.
The idea of oceans beneath the ice that might support life is far from the old paradigm. It opens up a whole new idea of how life might form in solar systems in the cosmos.
In the summer of 2019, NASA announced that it had approved a mission called Dragonfly that would return to the surface of Titan.
Dragonfly is a mission that's going to Titan to study its prebiotic chemistry. It's an octocopter.
By being a mobile lander, Dragonfly is going to allow us to truly discover what the surface of Titan is like.
And it would spend most of its time on the surface making scientific measurements, but then we'd be able to fly from place to place so that we could measure the chemistry in different environments.
Dragonfly's main goal is to taste the surface of Titan and tell us what the end product of all of this fantastic chemistry that Cassini revealed is.
And really understand how far prebiotic chemistry can progress in an environment we know has all the key ingredients for life.
Dragonfly is scheduled to leave Earth for the Saturnian system around 2027 and should arrive at Titan in 2035. Nearly 55 years after Pioneer 11 gave us our first encounter with Saturn.